Okay, so last time we just stopped here. So actually, here we talk about when the physician find out the relationship between the resistivity and the temperature. Okay, and the temperature. So at that time, they also find how to generate liquid helium so that they can achieve very low temperature with some pressure manipulation. Okay, by using the PVNRT, then they can achieve very low temperature, like 1 Kelvin or sub 1 Kelvin. Okay, so they are able to achieve this kind of superconductor. Okay, so when the temperature is sufficiently low, okay, then the material suddenly have no resistance, okay, become a perfect conductor, so that there's no resistance, so there will be some discontinuity near the very low temperature. Okay, so here there is a table about the resistivity for different material here. So on the top part is typical metals. Okay, so we have silver, copper, gold. Okay, so if it is at home, probably we'll use copper as the wire. So because conductivity is I mean the resistivity is pretty low, and in the experiment, okay, in the laboratory, we sometimes may use silver or sometimes may use gold. Okay, even though the gold has quite a bit larger resistivity. Okay, but the gold won't oxidize. Okay, so that means it will be better. Okay, for the copper, even though it's not that easy to rotten, okay, but still it may be. Okay, it may be sometimes. So for the laboratory, silver and gold may be a better option. And actually, the aluminum is has an even higher resistivity. Okay, and so on and so forth. And actually, the metal, the iron has a quite high resistivity, and also the platinum. Okay, so at the bottom part, we have the insulator. Okay, insulator. Okay, we have a glass, we have a fused quartz. Okay, fused quartz 10 英. Actually, this is much higher than the metal. Okay, so you can see you only need to see the exponent. Okay, so this is 10 to the -8. This is 10 to the 10th, a positive 10, 10 to the 14. Okay, 10 to the 16. Okay, so you see what is the difference between this kind of conductor and insulator. Actually, it still have the resistivity is still finite, so there might be some very small current. Okay, but the point is the voltage, okay, or the potential difference need to be sufficiently high so that the current might still go through the typical insulator. Okay, so that maybe when you have a screwdriver, it tells you that, okay, under how many voltage you're safe to use. But if it is higher than that threshold voltage, then okay, it is still it will still be danger. Okay, so in the between we have a typical semiconductor. Okay, so this is generally used for the IC. Okay, so you can see silicon pure. Okay, or pure silicon. Okay, so the resistivity is 10 to the third power, pretty high. Okay. 11th order, okay, larger than the typical metals. Okay, so we won't use pure silicon to make the IC. Okay, so but before making the IC, we need to have the pure silicon, and then we try to add some electron, or maybe we add some 3A element or 5A element, okay, to the pure silicon, so that we can create some so-called N-type semiconductor or P-type semiconductor. Okay, the P-type semiconductor is using the pure silicon, adding the 3A, okay, adding the 3A, so that the outer layer, okay, will have one less electron, okay, so that other electron may be able to enter the outer layer of the electron. So there are quite a bit of conductivity here. Or for the N-type semiconductor, we try to add some 5A, okay, 3A, okay, I mean 3A or 5A, okay, on the periodic table, okay, so that yeah, it could have some sort of low resistivity. Okay, although it is three or four order higher, or 4 or 5 order higher than the metal, but the semiconductor or P-type N-type semiconductor have some nonlinear effect. Okay, nonlinear effect, so that we may be able to use the voltage to control the resistance of the modes, okay, of the semiconductor device itself. Okay, so in IC design, we generally use the CMOS, okay, the CMOS, complementary metal oxide semiconductor, okay, for IC design. So of course it consists of PMOS or NMOS. The P-type metal oxide semiconductor, N-type metal oxide semiconductor. Okay, so we generally call it NMOS, PMOS. So by using both NMOS, PMOS, we can create some digital logic, or maybe use for some analog circuits. Okay, so yeah, so what we really need is the nonlinearity of this PMOS and NMOS. Okay, of course for the metal, okay, it has a much lower resistivity. Okay, but it cannot be controlled. It is quite linear. So after the shape is there, so the resistance is fixed. Okay, you cannot control the resistance of a wire. So we need the semiconductor to create some more complex circuit. Okay, so here we have a sample problem. So here it says a rectangle block, okay, of iron. A rectangular block has dimension 1.2, 15 centimeter cube. A potential difference is applied to the block between the parallel side in such a way that those sides are equipotential surface. So what is the resistance? Okay, what is the resistance of the block if two parallel sides are two square ends with dimensions 1.2 times 1.2 centimeter square? And then the second case is two rectangular sides, dimension 1.2 times 15 centimeters square. Okay, so for the first case, it is like we try to use it properly. Okay, we try to use it properly, something like this. Okay, so this is the 1.2 times 1.2. Okay, like this. So actually the cross-section area will be like 0.012, okay, 1.2 centimeter. Okay, becomes 0.012 meter square. Okay, so which is 1.44 times 10 to negative 4 meter square. Okay, so R will be rho L over R. Okay, so which is 9.86, 9.86 times 10 to negative 8th power times 0.15. Okay, 0.15. Okay, so this is 1.2, 1.2. This is 15. Okay, all are in centimeters. 1.44 times 10 to negative 4. Okay, so this is pretty easy. So 100 mil ohm. Okay, 100 mil ohm. Okay, so this is quite a small resistance here. Okay, so this is the first one, and the second one is the second case will be like something like this. Okay, so this is 1.2, 1.2, and then we try to use it like this. Okay, we try to use it like this. So for the cross section area, okay, here it will be like 0.012 times 0.15. So this is 1.8 times 10 to negative 3rd power meter squared. So in that case, R will be rho over L, rho L over A, which is 9.86 times 10 to the negative 8th power times 0.012. Okay, so this will be the length. Okay, so over 1.8 times 10 to the negative 3rd power. So which is 0.65 micro ohm. Okay, so this is even smaller, yeah, because the cross section area is much larger and the length is much shorter, so the overall resistance will be much smaller than the first case. So this is pretty easy to just let you know how to plug in some number into this R equals rho L over A formula. Okay, so next part will be the Ohm's law. I think in high school physics probably you already know what is Ohm's law. So yeah, originally there are quite a lot of text on this page, but simply speaking, it is nothing but V equals IR. So I don't try to go through all the text behind. So the idea here is like we have a resistance. Okay, we have a resistance. Usually, for the circuit diagram, we will use the symbol like this to represent resistance. Okay, a resistance. And one small thing you need to pay attention is if we have some potential difference, like usually we will note it like this. Okay, so suppose we have a V here and then we a plus and then minus here, which means that this point has a slightly higher potential okay, on the left node than the right hand side node. So which means that let's say let's call it this is VA, this is VB. Okay, so which means that for this notation, which means that V is actually VA minus VB. Okay, so we use a positive sign and negative sign to denote which is positive, which is negative. Okay, and then if we are applying this V equals IR, which means that so the current is from the positive to the negative. Okay, so the I will be like this, which means that here, based on this definition of the potential, the potential, positive on the left side, negative on the right side. So the current will be from left to right. This direction and the polarity here, should match each other. Don't try to mix it up. Otherwise, you will have a negative side, and then further calculation won't be correct. So this is really the only important point. To apply the V equals IR, the Ohm's law here. So this is nothing but a line. Actually, even in high school mathematics class, you you know, okay, so this is a line, okay, going through the original point. Okay, so this is generally true for most of the metal, okay, even for inductor may also be correct. Okay, but for some semiconductor, okay, semiconductor device, this is not true. Okay, so figure C, okay, the bottom part here says here, so the figure C is a plot for another conducting device, actually a semiconductor device. So current can exist in this device only when the polarity V is positive and applied potential difference is more than about 1.5 volts, and then current does not exist when the relationship I and V is okay. So the relationship is not linear, okay, or non-linear, okay. So it depends on the value of the applied potential difference V, okay. So we will say this one is quite non-linear, okay. So which means that if the potential, okay, if the potential is negative, there won't be any current. If the potential is positive or at very least higher than 1.5 volts, okay, it will be like an exponential increase. Or for some of the simplified circuit model, it will look only like okay, 0 for the negative part, and then go straight up to infinity, okay, like this. Okay, we won't have any value on the right side. Okay, actually, who knows what is this device? Okay, what is this device? When I asked the ECE student in the past, okay, they probably can answer. Okay, so actually this one is called a diode. Diode. In Chinese called 二极体. 二极体. Okay, so this is a simplified model, or maybe for some of the other models, okay, so it will be like this is like an exponential function, exponential to something, okay, exponential to something. Yeah, so this will be quite non-linear. Okay, we will say actually this is the current, this is the current, this is the voltage. So which means that if we take the derivative of this curve, okay, and then take the reciprocal will be the resistance. So which means that for this region, okay, this region, the resistance will be infinity, okay, because if we take the derivative here, this is flat, the slope is 0. The slope is 0. So take the reciprocal will be the resistance. Okay, the resistance will be like dVdI. Okay, dVdI. Okay, if it is not a linear curve. Okay, so it could be like 1 over di dv. Okay, for this case. So you take the derivative. Take the derivative of this line and then take the reciprocal. So here the slope will be like this. Okay, the slope will be like this. Take the reciprocal will be the resistance at that point. Okay, so it will be finite. Okay, anyway, so let's go to the next part. Okay, so yeah. So here is the Ohm's law in a microscopic view. Okay, so in previously, okay. So this is called the Ohm's law, which means that they try to have a circuit, okay, have a circuit element like this, and then they try to apply some different potential and then measure the current, something like this, and then try to plot quite a lot of dots, okay, to change the current and or change the potential to measure the current, and then try to do quite a lot of different value, and then okay, they find that okay, this is like a straight line, so they try to write out this Ohm's law. But this is just a correlation. Okay, this is just a correlation. So physician usually try to find some other point of view so that to explain why this could be true. So here is a microscopic view from a totally different point of view. Rather than doing the experiment, they try to use some theoretical interpretation so that they try to come up with a similar idea. So here the idea is like starting from a point, okay, probably point A, okay, there is an conduction electrons, okay, there are quite a lot of conduction electrons in a material, or actually in a conductor, okay, or in a metal. So are free to move, okay. So like molecules in gas leads to an expression for the resistivity of a metal. So if an electron of mass m, okay, is placed in an electric field of magnitude E, okay, so the electron will experience an acceleration, okay. So this is trivial. So the magnitude of the acceleration A will be F over m, okay. So according to the Newton's second law of motion, okay, Newton's second law of motion, A equals F over m, and then F will be E times E, okay, so nothing special here. So here it also assumes the drift speed is Vd, okay, so which will be roughly A times tau, okay. So what is A, what is tau? A is actually this acceleration. So at the very beginning, it tried to assume that, okay, this electron is totally at rest, okay. So it's there will be force, okay, accelerating this electron, okay. So on average, okay, so the tau is actually the average time between collisions. So which means that, okay, so the A is so the electron is probably starting at A, so that is accelerate. Okay, probably it will go to here, okay, until it hit another, hit something else, okay, hit another electron, or maybe hitting the some other nucleus, okay. So and then it collides, okay. So it stopped here, and then it will start to accelerate again, okay, and then maybe a second collision, and then so on and so forth, okay. So okay, each time, each collisions, okay. Every two collisions, okay, have a different time, okay. So on average, we call it tau, okay. We call it tau, which is the average time between collisions. So which means that probably the electron will start from zero speed, okay, accelerate up to A tau, okay, accelerate up to A tau. So in that case, we try to plug in A to here, okay. So which means that we put this one to here. So here we have Vd equals E over m, and then times tau. Okay, so in this case, we also apply J equals Ne times Vd. Okay, this is what we learned before. Okay, so in that case, we can plug in this one to here. So we have a NEEM times tau. Okay, so also we have this one. Okay, so in that case, okay, we come up with something like, okay, we try to go from here to here. So which means that we remain E, okay. So maybe I use another curve, okay. So we remain E, okay, on one side, and then we put all other variable to the other side. So which means that this m, okay, this m will go to here, and then we have E square go to here, we have N go to here, we have tau go to here. Of course, we have a J on the other side. So which means that from here to here is nothing but some algebraic computation. So it means that we have E equals something times J, okay, something times J. So what is this something? This something, okay, previously we have this so-called vector form of the Ohm's law, which means that it should be equivalent to the Ohm's law. So if we assume this is true, by comparing these two, okay, we will have rho equals m over e squared. Okay, we don't have this j here, okay, we don't have this j here. So m over e squared and tau. So what are these? Okay, m is the mass of the electron, so which should be a constant. And then e squared, okay, e is the elementary charge, also a constant. And then n, okay, n is the charge density, okay, the volume charge density. So it is only related to the material itself, okay. So for a specific material, this n should also be a constant, but will be different for different material, okay. So and then the tau should also be related to the material itself, because for a specific material, it has a specific structure, okay, the distance between atoms and atoms. So the tau would also be only related to the material, yeah, but keeping it a constant for the same material, okay. So which means that these two terms are generally constant, and then these two terms, okay, these two variables only relate to material. So it actually explains, okay, why given a specific material, the resistivity could be a constant. Okay, so this is the resistivity, and then by changing the material, okay, this rho will also change. Okay, so this actually explain, okay, why there will be resistivity. Okay, so here, okay, by having this interpretation, okay, of course it may not be absolutely true, okay, because we assume quite a lot of approximation here. So yeah, the model is quite simplified. So but at very least, based on this interpretation, we tend to believe the Ohm's law could be true. Okay, so here we have another sample problem. Okay, so here it says what is the mean free time tau between collisions for the conduction electron in copper. So it is actually tau equals m over n e square rho. Okay, so this is nothing but this one. Okay, this one, or actually tau. Let me see. Okay, actually using this one. Okay, tau equals, okay, moving the E over M to the other side. Or, yeah. Okay, so actually we can plug in all the numbers. Okay, so electron, the mass of the electron 9.1 times 10 to negative 31. Okay, and then N is 8.49 times 10 to 28th power, and then E squared 1.6 times 10 to minus 19 square, and then rho is this one, or 9.11. Okay, so whatever you like. So 1.69 times 10 to negative 8. Okay, something like this. So this is nothing but 2.5 times 10 to negative 14 second. Okay, or you can actually write it as 25 femtosecond. Okay, so both are okay. So yeah, so this time is extremely short. Yeah. So for question B, the mean three-path lambda of the conduction electron in a conductor is the average distance traveled by the electron between collision. What is the lambda for the conduction electron in copper, assuming that the effective speed V effective is 1.6 times 10 to the 6th power meter per second. Okay, so this is nothing but lambda equals V. Okay, lambda is the length. Okay, is the length. So V, okay, is the is the speed, okay, is the speed times the time, okay, times the time, so V times, so it is nothing but S equals VT, something like that. Okay, so this is 1.6 times 10 to the 6th power, and then tau is actually this one, 25 times 10 to negative 15 power. So this is nothing but 14 nanometer, 14 nanometer. Okay, so which means that every time when the electron travel for 14 nanometer, okay, on average, okay, the electron will collide with something, like maybe other electron or maybe the nuclear. Okay, so here it says, okay, so actually this sample problem is easy to compute. Okay, so this is not try to tell you how to calculate something. Okay, so the point is just to tell you some physics story. So the point here is that this 40 nanometer is about 150 times the distance between the nearest labor atom in a copper lattice. Okay, so yeah, so it means that thus on average each conduction electron pass many atoms before finally hitting one. Okay, before finally hitting one. So actually this story is try to tell you that okay, so at that time, of course, the physician won't have sufficient equipment to see, okay, what is really an atom. Okay, they cannot try to observe an atom. Okay, so of course they may. Okay, so when you learn chemistry class in high school, so probably you have you should have learned something like the chemistry. Try to imagine. What will be the inside? Okay, so probably at the very beginning they just consider, okay, so the material is like a cake. Okay, so every atom is quite large. Okay, something like this, quite dense. Yeah, because when you just pick up something, okay, it won't seem to be quite a lot of space in between. Okay, so they consider, okay, they may consider the lattice could be something like this. Okay, so there are only very small gap in between, but this one just tells you that, okay, it won't be true. If it is so dense, okay, it is not possible that the electron just go through quite a lot of atoms, okay, before collision. Okay, so probably, okay, there's some truths that, okay, so probably the atom should be like, okay, we have a nuclear in between, and then, okay, quite a lot of space outside should be empty. Okay, so and then the electron just grow, just rotate. Okay, the nuclear. Okay, so in that space. Okay, so it makes the lattice will be like, okay, so there are quite a lot of space. There are quite a lot of space in between, so that the electron can actually go through quite a lot, for even 150 atoms before a single collision. So this actually tells us this story. Okay, so here we talk about the power. Okay, the power. Okay, Chinese is 功率. Okay, so actually the power will be like P equals IV. Okay, so this is always true. Okay, this is always true for even for resistor or even for other device. P equals IV is always true, but P equals I square V or P equals V square over R, it only apply for the resistor. Okay, only apply for resistor. Okay, so you need to pay a bit attention to it. Sorry, this is not I times V. It should be I square R. Okay, it should be I square R. So because by applying V equals I out here, okay, by let's say eliminating V, okay, so which means that I out times I, okay, it would be I square out, okay, here. Or if we have, okay, if we try to eliminate I, okay, so which means that I equals V over R, putting it here will be V square over R. So these two only apply for resistor, but P equals IV apply for anything. Okay, so this is, yeah, so this is it. So this on the left side is just tells you that, okay, so this is the, okay, so this is the potential energy, the electric potential energy is actually nothing but dQV, okay, U is QV, so dQ will be like I times dt, okay, because I is dq dt, okay, I is dq dt, so you can say that, okay, dq is I dt, okay, I dt, okay, V is, we assume is a constant, so just put it outside. So find the IV dt, okay, and then integrating it will be like a P equals, or maybe like you're moving this one to the left side, okay, du dt will be the power, which is I times V, okay, so this is always true, okay, this is always true, this is like a definition. Okay, finally we try to talk a bit more about the semiconductor and superconductor in a very shallow way. So for the semiconductor, a material that have few conduction electrons, conduction, but can become conductor when they are doped, okay, with other atoms, okay, which means that we try to add some 3A or 5A, okay, 5A element into the pure silicon, okay. In Chinese we call it 掺杂一些杂质进去 ，OK， 加一些3A 族、5A 族的元素进去，让它变成那个3A 的话就变成 P 型的 semiconductor，OK， 加5A 的话它就会多出一个电子，就会变成 N type 的，加一个3A 的话它就会外层就会缺一个电子，就会有一个叫做电动的东西，就会有一个叫做后电动 ，OK， 就是缺一个电子，那其他电子就会可以补充过来，就是一个间接的方式，有一个自由电子的一个机制 ，OK， so we try to dope the pure semiconductor, okay, pure silicon, okay, to make it like P type or N type semiconductor. So in a semiconductor, okay, the N is small, number of free electrons is small, but increase very rapidly, okay, blah blah blah, okay, so okay, we have slightly talked about it in the previous table, so I don't try to repeat again. And for the super semiconductor, okay, so just as what I mentioned, okay, going to as low as 4K, okay, of course you cannot go read to 0K, okay, because it is the absolute 0 degree, yeah, so like negative 273 degrees Celsius, okay, so we can never achieve that, but the idea here is like yeah, at that part is like linear increase, but go down to a specific temperature for a specific material like this one, okay, the resistance suddenly disappear, okay, like this is like a perfect conductor, okay, so we call it superconductor, which means that the material that lose all electrical resistance below some critical temperatures. So most such material require very low temperature, but some become superconducting at temperature as high as room temperature. 那所以这个的话就是说，他们叫高温超导，其实他们是希望它能高温的，它不是真的高温，它其实是要很低温啊。但是他们希望找出一些材料的话，就是可以不需要到那么低的温度，因为如 如果要到4K 的话，它需要一些所谓的 liquid helium 液态氦才能够到达这么低的温度啊。那如果是高温的话，就是可能液态氮可能到负100多度那么样的甚至它有些情况他说有些是 room temperature， 但是一个条件是它要加很高的压力因为它有一个叫做 PV 的一个 NLT 嘛。高中应该 you should have learned this in a high school chemistry class. PV equals NLT. PV equals NLT. Okay, so this is constant. So it is like PV over T is a constant. It's a constant. It's a constant. So which means that if we would like to have a very low temperature, so rather than that, we try to increase the pressure, okay, and then maintain the T to be large, okay, so that it can still be true, okay. So this is the case. You can have a much higher temperature to achieve this superconductor phenomenon, but you need to apply quite high pressure for it. Okay, so maybe let's take a